Hello everyone, welcome to all in the next lecture of integral equations. Okay, so in the previous lecture we are going to discuss the homogeneous Fredholm integral equation, and also we solve, that is we find the solution of homogeneous Fredholm integral equation of second kind. Okay, so up to we see only the solution of, that is we see the methods to find only the solution of non-homogeneous Fredholm integral equation of second kind, and also in previous lecture we see the solution to find, that is we see the method to find the solution of homogeneous Fredholm integral equation of second kind. Okay, so up to all the lecture we see only the second kind Fredholm integral equation. Okay, so in this lecture, that is in today's lecture, we are going to discuss the Fredholm integral equations of first kind. Okay, so in first chapter we see what is the Fredholm integral equation of first kind, also what is the Fredholm-Volterra integral equation of first kind. That is, we know the standard form of the Fredholm integral equation of first kind. Okay, so in this second chapter we have to discuss the method for finding the solution of Fredholm integral equation of first kind. Okay, so first here I write the standard form of Fredholm integral equation of first kind. Okay, so we know that the standard form, so standard form of Fredholm integral equation of first kind is okay, we know that the standard form, that is f of x is equal to lambda integration from a to b k of x t into u of t dt. Okay, f of x is equal to lambda integration from a to b k of x t into u of t dt, where x belongs to domain. Okay, then which is the standard form, then here in this lecture we have to discuss how to find the solution of this integral equation. Okay, so there are many methods to find the solution of equation, solution of first kind Fredholm integral equation, solution of first kind Fredholm integral equation. Okay, but in this text we discuss, or we use the method, that is the method of regularization, Okay, so we have to use the method of regularization to find the solution of Fredholm integral equation of first kind. Okay, so method of regularization converts the Fredholm integral equation of first kind, to second kind. Okay, so using method of regularization, first we want to convert the first kind equation to the second kind equation, that is second kind Fredholm integral equation, either it is a homogeneous or a non-homogeneous. Okay, so and then we want to solve that equation. Okay, so in all previous lecture we see how to find the solutions of second kind Fredholm integral equation. We see all the methods. Okay, so using that any one of the method we can use and then find the solution of second kind. Okay, and from that we rewrite the solution of first kind integral equation. Okay, so we convert first kind Fredholm integral equation, that is u of x, that is f of x is equal to lambda integration from a to b k of xt into u of t dt to second kind. We consider u epsilon of x, epsilon into u epsilon of x is equal to f of x minus lambda integration from a to b k of xt into u of t dt. Take it as equation number 2 and first kind equation, that is the equation number 1. Okay, so in this way we have to get, this is the Fredholm integral equation of second kind. We consider in this form. Okay, or we can rewrite this as u epsilon of x is equal to f of x divided by epsilon minus lambda divided by epsilon integration from a to b k of xt into u of t dt. Okay, so here we have to get which is the second kind Fredholm integral equation. Then using any one of the method for finding solution of second kind integral equation, Fredholm integral equation, we use and find the solution of this equation, that is we find the value of u epsilon of x. Okay, and here if we take epsilon tends to 0. Okay, if we take epsilon tending to 0, then obviously we have to get the solution of integral equation of first kind. Okay, then to find using any one of the method to solution of equation number 2, that is u epsilon of x, and we get obviously solution of equation number 1 as tending epsilon to 0, because we consider here epsilon be a small positive parameter. Okay, epsilon be a small positive non-zero parameter. Okay, so here we use the any one of method, that is we have to discuss in previous lectures. We see all the methods, and using that any one of method we find the solution of second kind equation, that is we have to get the value of u epsilon of x, and if we take this solution as epsilon tends to 0, then obviously we want to get the solution of integral equation of first kind. Okay, that is the u of x. Okay, so in this way we can solve the Fredholm integral equation of first kind using the method of regularization. We want to only convert first kind to the second kind, and then we want to use the any one of method of solving second kind Fredholm integral equation. So we see one example on that. Okay, so see here I write the example. Okay, that is the Fredholm integral equation of first kind. Okay, integral equation of first kind. Okay, so here the example is combine the method of regularization and the direct computation method to solve the Fredholm integral equation of first kind. That is, we want to use first method of regularization to convert given first kind integral equation to the second kind integral equation, and then for finding solution of second kind integral equation we have to use the method of direct computation method, because for finding the second kind Fredholm integral equation, so for finding solution of second kind Fredholm integral equation, we see different methods. So from that we have to use here the direct computation method, because we want to give that in example. Okay, so first, by method of regularization, first take given equation as equation number 1, method of regularization. We convert first kind integral equation, first kind Fredholm integral equation number 1 to second kind Fredholm integral equation. Okay, so we consider the equation as epsilon u epsilon of x is equal to, we want to shift this function f of x on this side, so we have to get 1 by 2 e raised to 2x minus integration from 0 to 1 by 2 e raised to 2x minus 2t into u epsilon of t dt. Okay, here we want to consider also u epsilon of t into dt. Okay, here I can't write, so write here also the u epsilon. Okay, so we have to consider the u in terms of u epsilon. Okay, so in this way we convert first kind integral equation to the second kind Fredholm integral equation. Okay, then for solving the second kind integral equation, we have to use the method of direct computation method. If we have to not given in example the special method, then we can use any one of the method, that is we have to know. Okay, so here we use the direct computation method. Then by using direct computation method, to find solution of equation number 2, that is integral equation of second kind. So we consider integral equation of second kind will be in the form, if we observe again, for using direct computation method, the condition is that the given integral equation, Fredholm integral equation, is a non-homogeneous Fredholm integral equation, and also we can use the for homogeneous integral equation the direct computation method, and also the condition is that the kernel k of xt will be the separable form. Here kernel k of xt will be e raised to 2x minus 2t. Okay, so we can write this power separately. We have to get this as e raised to 2x minus e raised to 2x into e raised to minus 2t, that is which is the separable kernel in terms of x and t. So we use the direct computation method. Okay, so for using direct computation method, we can write equation number 2. Equation number 2 becomes a epsilon u epsilon of x, or we can shift this epsilon here. So we have to get here u epsilon of x is equal to 1 divided by 2 epsilon e raised to 2x minus, here integration from 0 to 1 by 2 e raised to 2x into e raised to minus 2t into u epsilon of t dt. Okay, so we can write this as 1 divided by 2 epsilon e raised to 2x into e raised to 2x minus, here also I miss the 1 by epsilon. Okay, because we shift this epsilon on in LHS in RHS, so which is divided to each term. Okay, so here also we get 1 by epsilon. Okay, so here e raised to 2x we take outside, which is constant with respect to t, so we get e raised to 2x divided by epsilon, and in integration 0 to 1 by 2 e raised to minus 2t u epsilon of t into dt. Okay, so then u epsilon x is equal to e raised to 2x divided by 2 epsilon minus e raised to 2x divided by epsilon, and here we consider this integral as a alpha by using direct computation method, because we separate in direct computation method the kernel and take the terms of x outside from integration. So remaining integral contains only the terms in terms of t, and take this integration as some constant alpha, that is alpha with the numeric value, because here we find the value of this definite integral, we have to get the numeric value. So alpha will be the constant. Okay, so we consider u epsilon of x is equal to this by using direct computation method. Okay, so we can write this as e raised to 2x. Here we take e raised to 2x outside, so we have to get e raised to 2x in bracket 1 divided by 2 epsilon minus alpha divided by epsilon. Okay, so u epsilon of x will be this. Then from that we can write u epsilon of t. U epsilon of t is equal to, we get e raised to 2t in bracket 1 divided by 2 epsilon minus alpha divided by epsilon. Okay, then okay, so here epsilon is equal to, we consider where epsilon is equal to, we consider integration from 0 to 1 by 2 e raised to minus 2t into u epsilon of t dt. Okay, so we put here value of u epsilon of t from the here. So we get 0 to 1 by 2 integration from 0 to 1 by 2 e raised to minus 2t, u epsilon t will be this. So we put here value, so this will be e raised to 2t and in bracket 1 divided by 2 epsilon minus alpha divided by epsilon into dt. Okay, then we solve this integral. Okay, so we get alpha is equal to, we take here 1 by 2 epsilon minus alpha by epsilon will be the constant, so we take this from outside, this will be outside from integration. So 1 divided by 2 epsilon minus alpha divided by epsilon, and in integration 0 to 1 by 2, here this e raised to minus 2t into e raised to 2t dt. Okay. Okay, so in integration remaining only e raised to minus 2t into e raised to 2t dt. Okay, so we have to get 1 divided by 2 epsilon minus alpha divided by epsilon, and here we get 0 to 1 by 2 e raised to 0 dt. Okay, so we get 1 by 2 epsilon minus alpha divided by epsilon. Integration from 0 to 1 by 2 e raised to 0 will be 1, so we get here only dt, that is 1 divided by 2 epsilon minus alpha divided by epsilon. Integration of dt will be t, limits from 0 to 1 by 2, so we have to get 1 divided by 2 epsilon minus alpha divided by epsilon into 1 by 2 minus 0, that is we get 1 by 2 epsilon minus alpha divided by epsilon into 1 by 2. Okay, alpha is equal to, we get this, but here we want to find the value of alpha. So alpha, here we multiply this 1 by 2 inside the bracket and shift these terms in LHS, so we get alpha minus alpha divided by 2 epsilon, not minus, this becomes a plus on this side. Okay, then is equal to 1 by 4 epsilon, 2 into 2 becomes a 4. So here we take cross multiplication to get 2 epsilon, or if we take outside we get 1 upon 1 by 2 epsilon is equal to 1 by 4 epsilon. Okay, so next by solving this we have to get epsilon in bracket 2 epsilon plus 1 divided by 2 epsilon is equal to 1 divided by 4 epsilon. Okay, so we get epsilon is equal to 1 by 4 epsilon into, we shift this term in RHS to get 2 epsilon divided by 2 epsilon plus 1. So epsilon gets cancelled, 2 2s are 4, so we have to get epsilon is equal to 1 divided by 2 in bracket 2 epsilon plus 1. This is the value of alpha. Okay, we have to get value of alpha, then we put value of alpha in u epsilon of x to get the solution of equation number 2, that is second kind integral. Okay, And then from that we have to take the epsilon tending to 0 to get the solution of first kind integral. Okay, so we put alpha in u epsilon of x. So u epsilon of x is equal to be consider epsilon of x is equal to be consider 1 by 2 epsilon minus alpha divided epsilon into e raised to 2x. Okay, so we put here value of alpha. So 1 by 2 epsilon minus alpha will be this 1 divided by 2 into 2 epsilon plus 1 into this epsilon into e raised to 2x. Here we take the cross multiplication and simplifying this bracket because we have to take here epsilon tends to 0. So we simplify. So we have to get here in LHS this 2 epsilon in bracket 2 epsilon plus 1 minus into this 2 epsilon divided by 2 epsilon. This 2 epsilon into 2 epsilon becomes a, or we can write this in next step 2 epsilon into 2 epsilon in bracket 2 epsilon plus 1 into e raised to 2x. Okay, so we have to get is equal to in numerator 4 epsilon square 2 epsilon into 2 epsilon 4 epsilon square plus 2 epsilon minus 2 epsilon divided by 4 epsilon square in bracket 2 epsilon plus 1 into e raised to 2x. Okay, so this plus 2 epsilon minus 2 epsilon gets cancelled and we get here next step 4 epsilon square divided by 4 epsilon square 2 into 2 epsilon plus 1 e raised to 2x. Okay, so this 4 epsilon square gets again cancelled and we have to get u epsilon of x is equal to u epsilon of x is equal to e raised to 2x divided by 2 epsilon plus 1. Okay, then which is the solution of equation number 2, that is second kind Fredholm integral equation. Second kind Fredholm integral equation. Okay, then from that we take epsilon tends to 0 to get solution of equation number 1, that is first kind Fredholm integral equation. First kind Fredholm integral equation. Okay, so we take limit epsilon tends to 0 u epsilon of x, that is we have to get u of x. So u of x is equal to limit epsilon tends to 0 u epsilon of x is equal to limit epsilon tends to 0 e raised to 2x divided by 2 epsilon plus 1. So by putting here epsilon tends to 0 e raised to 2x we take outside from limit. Okay, which is constant, so 2 into 0 plus 1, then we have to get is equal to e raised to 2x. So u of x is equal to we get e raised to 2x, then is the exact solution of equation number 1. Okay, so in this way we can find the solution of Fredholm integral equation of first kind by using method of regularization and direct computation method, that is we combine here two methods. Okay, here note that again if we solve this second kind integral equation by any another method, that is we know, because we know that there are different methods for finding the solution of second kind non-homogeneous Fredholm integral equation with separable current. If we use the another method, that is if we use suppose the Adam decomposition method, then we want to get the different solution. Okay, and okay, so here note that the Fredholm integral equation of first kind have more than one solution also. Okay, either one solution or more than one solution also exists. Okay, then we see the next example. Okay, so see here I write the example. Combine the method of regularization and the Adam decomposition method to solve the Fredholm integral equation of first kind. Okay, first Okay, so first take the given integral equation as first kind integral equation as equation number first. So here we want to use the method of regularization and the Adamant decomposition method for finding the second kind integral equation. Okay, using regularization we have to first convert first to second kind, and for solving second kind integral equation we have to use the method of Adamant decomposition method. Okay, so first use method of regularization, use method of regularization to convert the first kind integral equation, Fredholm integral equation to second kind. Okay, so we consider the second kind integral equation in the form u epsilon u epsilon of x is equal to, we shift this term here, that is we get 1 by 5 into x minus integration from 0 to 1 x into t u of t dt. We consider here u epsilon of t dt. Okay, so we have to get, this is the second kind integral equation we consider in terms of u epsilon. Okay, then again we can rewrite this as u epsilon of x is equal to 1 by 5 epsilon into x. We shift this epsilon here. Okay, so and we have to get 1 by epsilon here, integration from 0 to 1 x into 2 t u epsilon of t dt. Okay, then to find solution of equation number 2 we use Adamant decomposition method. Okay, we use the Adamant decomposition method. Okay, so we know that, very well known that what is the Adamant decomposition method. In Adamant decomposition method we find the series solution components, that is we consider the solution in terms of series. Okay, that is first we want to find the components u0 of x, u1 of x and up to so on, and then we have to take their addition and which is the solution. So here we consider first the solution will be in series form, that is by Adamant decomposition we find the solution. So consider solution of equation 2 is, of equation number 2 is u epsilon of x is equal to summation n is equal to 0 to infinity u epsilon n of n, u epsilon n of x, n varies from 0 to infinity. Okay, so take first component of series solution, take first component of series solution, that is u epsilon 0 of x, u epsilon 0 of x is equal to f of x. We consider first component of series solution will be u epsilon 0 of x is equal to f of x, and here f of x for the second kind integral equation will be 1 by 5 epsilon into x. Consider this equation. Okay, if we compare this with the standard non-homogeneous Fredholm integral equation, then we get f of x will be this. Okay, here u of x is equal to f of x plus lambda integration from a to b k of x t into u of t dt. This is the standard form. We compare this with this, then we have to get f of x will be equal to 1 by 5 epsilon into x, which is the first component of series solution u epsilon 0 of x. Okay, then to find next components using recurrence relation u epsilon n of x is equal to lambda integration from a to b k of xt into u epsilon n minus 1 of x into, not x here, u epsilon n minus 1 t into dt. Okay, so for n is equal to 1, n is equal to 1, we have to get u epsilon 1 x is equal to lambda. For this integral equation will be minus 1 by epsilon, so minus 1 by epsilon integration from 0 to 1. Okay, k of x t kernel will be, or we can just write here from this integral equation values of f of x. Here f of x will be 1 by phi epsilon x, lambda will be minus 1 by epsilon, and k of xt will be x into t. By comparing this with the standard non-homogeneous Fredholm integral equation, we have to get this value. So kernel k of xt will be here x into t, and here we have to get n minus 1 minus 1 0, that is u epsilon 0 t dt. Okay, then we put here value of u epsilon 0. So minus 1 by epsilon integration from 0 to 1 x into t. Here u epsilon 0 of x is equal to, we consider this. So we have to get from that u epsilon 0 of t is equal to 1 by 5 epsilon t. Okay, so we put this value here. We get 1 divided by 5 epsilon into t dt. Okay, so we take here 1 by 5 epsilon and x outside, because which is constant, so we have to get minus 1 divided by 5 epsilon square into x. Integration from 0 to 1, t into t becomes a t square dt. Okay, so we have to get here minus 1 divided by 5 epsilon square into x. Integration of t square will be t cube divided by 3, limits from 0 to 1. Okay, then we solve this integral. So we have to get u epsilon 1 of x is equal to 1 divided by 5 epsilon square minus 1 divided by 5 epsilon square x. By putting limits, we get here 1 by 3 minus 0 divided by 3. Okay, so we have to get minus 1 divided by 5 epsilon square into x into 1 by 3. This becomes a 0. So we have to get minus 1 divided by 5 into 3 will be 15 epsilon square into x. Okay, we have to get value of u epsilon 1 of x. Okay, then using this second component, we want to find the third component. Okay, so from that we have to get u epsilon 1 of t, that is in terms of t will be minus 1 divided by 15 epsilon square into t. Then for n is equal to 2, in equation number recurrence relation, we want to get u epsilon 2 of x is equal to lambda. We can write directly minus 1 by epsilon integration from 0 to 1 x into t, and here u epsilon 1 of t dt. Okay, so we put here values minus 1 by epsilon integration from 0 to 1 x into t. U epsilon 1 of t will be minus 1 divided by 15 epsilon square into t. Okay, dt. So again here x minus 1 by 15 epsilon square will be constant with respect to t. So we take outside, this minus minus becomes a plus. So we have to get x divided by 15 epsilon cube. Epsilon square into epsilon gets epsilon cube. Okay, and in integration 0 to 1 t into t becomes a t square dt. Okay, so by taking integration we get x divided by 15 epsilon cube t square, integration of t square again t cube divided by 3, limits from 0 to 1. Then by putting limits, we want to get the second component, the series solution. Okay, so we get u epsilon 2 of x is equal to x divided by 15 epsilon cube, and by putting limits 1 by 3 minus 0 by 3, that is we get x divided by 15 epsilon cube into 1 by 3, that is x divided by 45 epsilon cube, which is the u epsilon to x. Okay, so continuing in this way, if we find the next component, Then we want to get the next component by comparing with these components u epsilon 1, u epsilon 2 and u epsilon of x. We have to get next component u epsilon 3 of x is equal to x divided by here 45 into 3. 45 into 3 and we want to get here power of epsilon will be epsilon raised to 4. Okay. For epsilon, that is for second component, we have to get power of epsilon will be 2. For third component, we have to get power of epsilon will be 3. So for fourth component, we get here next power of epsilon raised to 4. So continuing in this way, we have to get the next components of series solution, and then to get solution by taking addition of all these components, by taking addition of all these components. Okay, so u epsilon x is equal to, we get u epsilon 0 x plus u epsilon 1 x plus u epsilon 2 x plus u epsilon 3 x and plus up to so on. Okay, so we put here values. We have to get u epsilon 0 of x will be, we consider 1 by 5 epsilon into x. Then u epsilon 1 x we have to get minus 1 divided by 15 epsilon square into x. Then u epsilon 2 x we have to get x divided by 45 epsilon cube. Okay, then we have to get next term will be minus and plus up to so on. In this way we have to get the alternate series. So from this we take here x divided by 5 epsilon outside, because which is common for each term, so we take outside. So we have to get the series 1 minus 1 divided by 3 epsilon. Here we take 1 epsilon outside and take 5 outside, so get 3 remaining, plus we want to get here 1 divided by, so 1 divided by 9 epsilon square minus up to so on. Okay, then we simplify this series to get the solution of equation number 2. Okay, so we have to get u epsilon x is equal to x divided by 5 epsilon. Okay, and rewrite this series as minus 1 by 3 epsilon plus 1 divided by 3 epsilon square, then minus and up to so on. So we want to get the alternating series. We use here for writing the function, we use this series 1 divided by 1 plus x. Series expansion of 1 upon 1 plus x will be 1 minus x plus x square minus x cube plus up to so on. So here we consider x is equal to 1 divided by 3 epsilon. Okay, so using this we have to get x divided by 5 epsilon, and which is the expansion of 1 upon 1 plus 1 by 3 epsilon. Okay, x is equal to, we consider 3 epsilon. So by simplifying we get x divided by 5 epsilon. We are taking cross multiplication, 3 epsilon plus 1 divided by 3 epsilon. So 1 divided by 3 epsilon plus 1 divided by 3 epsilon. So we have to get x divided by 5 epsilon into, this becomes getting numerator. So 3 epsilon divided by 3 epsilon plus 1. So this epsilon gets cancelled and we get 3 by 5 x into 1 divided by 3 epsilon plus 1. Okay, this is the value of u epsilon of x, and which is the solution of equation number 2. Okay, then take epsilon tends to 0 to get solution of equation number 1. Okay, so by tending, that is we get u of x is equal to limit epsilon tends to 0, u epsilon x is equal to 3 by 5 x into x, limit epsilon tends to 0, because here 3 by 5 into x will be constant. So we take from outside from limit will be applied only for 1 upon 3 by 5. 3, 1 divided by 3 epsilon plus 1. Okay. So we have to get u of x is equal to 3 divided by 5 into x, and take here epsilon tends to 0, we get 1 upon 3 into 0 plus 1. 3 into 0 will be 0, 0 plus 1 will be 1, so 1 by 1 will be 1. So we have to get here 3 by 5 into x. U of x is equal to this. Is a solution of equation number 1. That is, which is the exact solution of given first kind Fredholm integral equation. Okay. So in this way we solve the solution or find the solution of solution of first kind Fredholm integral equation. Okay. So today we will stop here. Thank you.